Okay, so what is electricity? You missed the first part of the lecture because I didn't turn on. Well, in order to know what electricity is, first thing we have to do is we have to talk about the atom. You've heard of an Adam's apple? It's nothing like that. All right. So an atom is the most basic building block of all matter. So I think that's actually in the Q&A. The most basic building block of all matter. And if we were to draw in a very crude and one-dimensional way, we have in an atom, first thing we have is a nucleus. That's the center. That's like the nougat center. The nucleus. And inside of the nucleus, I'm going to need some different colors over here. Inside the nucleus, what do I want? There. We have a couple of things in here. We're going to say we have a proton. We'll give it 2 protons. And we have something called a neutron. So proton. So we'll do this one. This is the this nucleus is the center. I'll get around to that. We have a neutron. And back to red. And we have protons. Back to black here. All right, so inside that we have the nucleus. So we got the nucleus in there. And inside, well, the nucleus is the center of the atom. Can do this correctly and spell nicely. Center, C-E-N-T-E, center of the atom. And let me see what else. Oops, I want to use Roman numerals. That's what I want. It contains protons and neutrons. And protons are positively charged. Why are they a positive charge? Well, a long time ago, somebody just found these things and said, I'm going to call that positive. And from there on, it became. It wasn't like they really had a meter and they could figure it out and put it apart and go, ooh, that's positive. It's just, it has a charge, and we call that positive. And that's why I made it in red. And neutrons are neutral charged. They don't have a charge. And the interesting thing about atoms, for the most part, not all of them, is the number of protons. Number of protons equals the number of neutrons.
Usually.
I just said that. Unless we get into isotopes and ions and things like that. But we're not going to worry about that. We're just moving kind of slow here. Right? So everybody's on the same page here. So we've got that going on. All right. Now, outside of this, who watches Big Bang Theory? All right. So every time they change the screen, they have a little drawing of something. What is that little drawing and the thing's going around? That's an atom. All right. So that's more of a 3D representation of an atom. And those things that are going around are electrons. And they kind of move around in kind of a weird looking orbit. And if you're going to follow me along here, because I can't draw 3D, and if you look in your book, they're going to give you a nucleus, and then they're going to say, well, the orbits around like that, more like the moon goes around the Earth. Yeah, the moon goes around the sun. The moon goes around the Earth in a very one-dimensional. All right, but then you watch Big Bang Theory, and then it goes around in kind of a 3D fashion. Everybody follow? Well, neither one of those are actually correct. There's a probability theory of where these electrons go, and they buzz around, and that's getting way beyond this class. So just so you know that they don't really just circle like a little planet or a moon going around a planet or something. They're actually buzzing around. But for simplicity's sake, we just say that they're floating around like that. Yeah?
Isn't it kind of like a cloud? That's what they're thinking it is.
That's a model. It's a model for it.
Yeah. So and there's it's not really a cloud, but it's a probability where the one is buzzing around and where it's going to be. But anyway, way beyond the scope of where you need to be an A&P. So what you need to do to be an A&P is you got to get the concept and go with it. But what I like to kind of let you know, hey, it goes beyond this, so that you don't go out there and go, well, I just learned how an electron goes, and it goes like this. And then somebody say, who told you that? Well, now you can say, it's close enough, for what I'm doing. So, all right, so we have, so interesting enough, if I have 2 protons and 2 neutrons, I would also have
2 electrons.
2 electrons going around out there. All right. And we'll just put them like that, going around that little orbit. Now we'll come back over here. We're going to write about electrons. So electrons orbit the nucleus in what are called shells. Shells. So really a shell is nothing more than this. This right here is the shell. So there you go. That'd be shell. That's number 1, not #1. And then there's going to be another shell out here that would have, if I add another proton, it's going to be out here. And then there's shells that go all the way out here. And they keep going, and they go out, out, and out. And so the interesting thing there is, well, we can write, it's all interesting to me here. So electrons orbit the nucleus in shells. We got that. We'll just put this. That's a little plain. The number of electrons equals the number of protons. And the number of protons equals the number of neutrons. All right, so then it's, if we do that, then the atom it's a neutral atom, and we can say I don't want to say it's a normal one. If we add an extra electron, then it's a negatively charged ion. We start moving around, changing ions. Don't need to get into that, so we're just going to stop right there. Okay, so that's the basic atom. All right. I'll keep it simple here. All right, electrons. Electrons are fast. Electrons move at about the speed of light. If you're raising your hand to correct me, put it back down.
No.
Okay. Yes.
So since the number of protons equals the number of neutrons,
Uh-huh.
and the number of electrons equals the number of protons,
Uh-huh.
everything's equal.
Everything's equal. So if I got 2 protons, I must have 2 neutrons, so I must have 2 electrons. Right? Okay. What if I have 4 protons? 4 neutrons, 4 electrons. All right, you guys are smart. All right, electrons move at about the speed of light. How do I know that? Well, I put an electron here, and I timed how long it took it to get across the room with my stopwatch, which is about 186,000 miles per second. That's pretty fast.
I'm impressed with your stopwatch.
It took me 3 tries. All right. Depending on how many electrons there are. And how they are arranged, and how they are arranged, and how they are arranged around the nucleus, probably didn't need to write that, will determine if the atom makes up an insulator or a conductor. Insulator means no electricity flow. Makes up an insulator or conductor, which is electricity flow. Huh? Do I want you to draw them on the board? No, I do not.
What's the word after determine?
If the atom makes up an insulator or conductor. So an insulator is something that you want between you and electricity, right? So let's think about you plug in a light to the socket. What are you usually holding on to? Rubber,
The insulated coating.
an insulate, plastic, something along that nature. What's inside of it usually? Wires made out of copper, all right? So copper, some homes are made with aluminum. You don't want that house. Gold, silver, things like that. So I'm telling you, depending on how many electrons there, well, let me think, do I want to get into that? Yeah, we'll do that right now. So depending on how they're arranged. So the arrangement is a formula called 2n squared. I know, I'm getting into math right now. All right, and what that is 2 is a constant. So it's 2 times the number, and number of the shell squared. So if I want to know, and that tells me equals how many electrons are in a given shell. No, that's not how many. What is the maximum number? The maximum number of electrons in a given shell. There we go, the maximum number. So if I have my nucleus there, and here's the shell, and that shell, which number shell is that? Okay, so that's shell number 1. Well, now I'm going to ask you, what is the highest number of electrons we can have in that? All right, so now we're going to do the formula. 2, n is what number? Times 1 squared is what that is. Now I'm going to take a step back for a minute. I'm going to tell you, when we do something like this, we have to use the please excuse my dear Aunt Sally. All right? Which means that we do everything in parentheses first. Do I have parentheses? I did not the way I wrote it. Exponents, which I do right there. Multiply and divide. Now multiply and divide, I want you to be very careful. These really belong on the same level. Okay, same level. Left to right. So don't do times first and then division next. If it's written out, you go left to right. And A is addition. And S is subtraction. Same thing. Same level. Left to right. All right.
I have a question.
Yeah.
For the nucleus,
Uh-huh.
we said there could only be 2 of the it's neutrons, right?
I didn't say they're going to be 2. It matches. In the nucleus, if I have 10 protons, how many neutrons would I have? There you go. Just like that. All right? Mine just had 2. All right, so let's solve this. So I have to do my exponent first. So 1 squared is the same thing as 1 times 1. Now, if you don't know that, that's okay. Calculator. There's an x squared button right there. Well, you want, so I can do 1, x squared is 1, times 2 equals, and I get 2. So the number 1 shell, we'll do it right here. Number 1 shell has a max electrons of how many? 2. Well, what about the number 2 shell? So I will do 2 x squared times 2 equals 8. Number 3 shell. Everybody following along and can do this? Okay. 18 is the answer somebody shouted at to me. Hope you're right. How many is 4? 32. All right, so you follow?
Wait, how do we get
Huh?
How do we get those numbers?
2 times x squared.
Okay, the one thing though is you have to really stick with me. I can't always go all the way back to the beginning.
Okay.
All right, so we've been talking about this for a while. I've replaced this. The formula is 2n2. N is the number in the shell. So this is 2, 1 squared. This is 2 times 2 squared. This is 2 times 3 squared. And this is 2 times 4 squared. I'm glad you brought that up, though, so I can put it like that. All right? Everybody follow? Okay. So now, I told you the way that they're arranged has to do with whether it's an insulator or a conductor, right? So a conductor has less than 1/2 the allowable electrons in the valence we'll call it shell. Valence shell is the same thing as saying the last shell. So less than half. And an insulator has more than 1/2 the allowable electrons in the valence ring. It's actually called valence ring, which is the last shell. Everybody with me so far? Let me give you an example. I'm going to scroll this down a little bit. If I scroll too fast, somebody has to say, scroll too fast. All right.
I'm not done writing my notes.
You think gold is an insulator or a conductor? All right, so let's take a look at gold. So gold. I will go copper first. So copper. So copper has 29 electrons. How many protons does it have? How many neutrons does it have? All right. So it's arranged like this. So in, what are we doing? Copper. How many electrons can I have in the first shell? 2, and it does. It has 2. 1, 2. How many can I have in the third shell? I can have 8, and it does. It has 8. 1, 2, 3, 4, 5, 6, 7, 8. So 2, 8. What am I up to? 10? I got a ways to go, don't I? Third shell. How many's have in the third shell? How many can it have? What's the most? I'm hearing it. So 2, 8, 18. I'm just going to put 18. Has 18 out on this one. We're going to go all the way out to this shell. I've really got only one left. It's got one out here. How many can it have out in this valence ring? This fourth one? It can have 32. How many does it have? Is that less than half? That's easy math, right? That's what makes it a good conductor. See, we've got this one lone electron way out here. And when we come back and look back in the nucleus, what do I have in the nucleus? I had protons, which had a positive, and neutrons, which had, I'll put a 0 for no charge. So this has a positive charge down in here, this proton. And here I've got this electron way out here. And what happens is opposites attract. Heard the saying? Well, whoever said that, they were talking about electricity. Yeah.
I'm really confused. So you put 6 on the ones outside, or outside the nucleus, you have 18, you have 1. That only leaves 27.
It's 2, 8, 18, and 1.
Oh, okay.
8, 18, and 1.
So there's 2, 8, 18, and then 1.
Why is there one at the end?
Because that's the way God made it. I don't know. It's really the way. When you take an atom and you look at it under a electron microscope, and they see these atoms that make up copper, that's what it looks like.
So
Because there's 29.
the fifth shell always has one.
No, the fifth shell does not always have, unless it's copper.
You have to do the formula.
Okay, the one rule I've got here is you think he can understand it when all 5 of us are yelling at him?
No,
So only one of us can be a teacher at a time. Who wants to be it today?
I delegate Kevin.
Okay. Anybody second the nomination? All in favor? All right. All right. But there are times when I won't understand a student, and I will ask you guys. Somebody translate, and then you guys will tell me, and then we'll do it. Okay, so it's not always bad. All right. Did your question get answered?
Sorry.
Sort of. All right. So is there always one electron out in the fifth ring?
For copper.
If it's copper, it is, but only for copper. All right. If I look at something else, it's going to be made up different. This is what a copper electron looks like. This is what it looks like. All right. So it's got 29 electrons, 29 neutrons, all packed around in the nucleus, and then it's got 2 in this ring, and then it's got 8 in this ring. It's got 18 in this ring, and 1 out here. I like this one because what it did is it filled up each ring in order until it got to here, and there's one left over, so it has to go out here because this can't go in here anywhere because it's already full. Yeah,
So each ring can only have a certain amount, right?
that's what we talked about up here. Each ring can only have a certain amount. The first one can only have 2. The second one can only have 8. The next one can only have 18. The next one can have 32.
That's for everything.
That's the law. So that's for every atom out there, we'll say. All right? That we're going to talk about.
What's the name of this law?
I don't know.
Keep adding those rings until it equals
Do you know?
the
I
number
don't
of
know.
electrons. Right?
Okay, not necessarily. You would think so, and I certainly would have thought so. But let's take a look at something else. So, okay, that was copper. What's another good conductor?
Gold.
Gold. You want to do gold? Okay, I'm not going to do them all, so we'll do gold. Gold. Gold has 79 electrons. And I'm just going to write the numbers. The first ring has, next ring has, next ring has, next ring has, 32. Next ring has, how many? 50. Can have 50. Why? 1, 2, 3, 4. This is the fifth. The fifth, so it's 2, 5 squared. 5 squared is 5 times 5, which is 25 times 2. So it can have up to 50. But does it?
No.
It does not.
No less.
Gold. 18. Why? I don't know. It's the way God made it. And then it has 1. It's just the way it is. So that shows that you don't have to necessarily fill up. You don't have to fill up the ring before you go to the next one. How about silver?
Wait, how did you get 18?
I didn't. God made it that way.
So it would be.
What's the most it could have had?
50.
Most it could have has 50. That's not the way God decided to make it. He put 18 there. I will ask him one day.
The valence ring has 1.
If you want to know how you can ask too. Yes.
So he put 18 and then a 1 on the outer.
One on the outer.
So that makes it a good
So it would be
conductor.
19 then.
It's not 19. Could have been, but it wasn't.
It wasn't.
But that makes it a really great conductor because it has one lonely electron out here far away from the mothership. And when you start getting away from the mothership and they get lonely, they start looking for another home. All right, silver. So silver, I'll just do this real quick, is 2, 8, 18, 18, 1 again. Yeah,
Question. On the
fifth ring. Yeah.
Why could it only be 50 as the most?
Because the formula is 2n squared. N is the number of the ring.
Oh, okay.
That's the formula. That's why there's a fifth one here. The sixth would be 2 times 6 squared.
But if it was an insulator, it'd be half.
It would be more than half the allowable.
Okay,
We'll get this. So,
So it'd be like 75.
let's go. I don't have an example, I think, of an insulator. But let's just take any one of these. And let's just say whatever it is. Here's my last shell right here. That's the 6th shell. Okay?
You can do helium.
And I don't know off the top of my head. Well, helium is 2. Yeah. I kind of want to do this one, though. So let's just say that whatever this, say it's not gold now, it can have how many electrons out here? It could have 72 because it's 6 squared is 36 times 2. It could have 72. Half of 72.
96?
No, half of 72 is not 96.
36.
36. So let's say this number here was 38. Now it's got more than half the allowable, and so it would be an insulator. But,
Oh, okay.
all right, I'll do helium. Okay, so you follow?
Yeah.
Okay, these, and so what I want to tell you then is opposites attract, okay?
Sigma plus.
And so that means that the more, obviously, higher number of the half would be a better insulator. then?
Well, hang on, unlike charges attract. So a proton has what charge? And a neutron has negative. Did I say it? I meant electron. Electron has, so proton, positive, electron. Are they like or unlike? They attract each other. All right, so the closer they are, the more they want to attract in. So that's why all of these electrons, where is it? All of these electrons that are close in like to stay. And the further out it gets, the further that attraction is. And the more it's free to jump off and go somewhere else. And it's that electron moving is what electricity is. It's that electron out in that one. Oh,
That
free
number
one. Yeah, that number one in that. Yeah.
So typically, atoms with more protons are.
Not more. It could be though, because the further out you get in the shell. So yeah, we could say that. We look at copper, gold, everything else with more. Yeah.
Protons than other things that are.
Well, it's because we have more of them, we get more shells out the further away we are.
It's pretty complex.
So let's just take a look at what if we did this. So, all right, so unlike charges attract and like charges repel. So through the magic of my thing here, I've enlarged a piece of copper 100,000 times, a million times, and what I've got here is a bunch of atoms. These are all copper atoms, right? And that's all the nucleus, and that's the little orbit that what's orbiting around? My electron. Okay, so what happens is, if I take and I hook this up to a battery, so this is my gigantic wire, Now I'm going to now it's back to normal size. I'm going to hook up to a battery. I'll make my battery look like this. And I'm going to say this is the negative side, and this is the positive side. All right, it comes back around, goes to the positive side there. All right, so unlike charges attract and like charges repel. So I've got the negative side here, and what was the electron again?
Negative.
All right, I'll put a little negative sign for all my electrons. Hook up to a battery. Now I've got negative electrons over here flowing around, and they come to here. What's it going to do to this? Is it going to attract it or repel it? Hey, everybody says repel. So this is going to cause this electron to move over to here. This one's going to move over to here. This one's going to move over here. This one's going to move over here because it's that one electron out at the end. It's free to kind of move around. It doesn't really stick around at the mothership. But let's look at it this way. I've got a positive over here. Like charges, that's an unlike charge, right? So is it going to repel or attract? Attract. So this positive over here is saying, hey, everybody, come over this way. And all these negative ones over here are saying, well, you better go that way. I don't know why I'm personifying it, but I am. So that means that electricity is the flow of electrons. So electricity, well, it doesn't mean that. That's what it is. Electricity is the flow of electrons. So electricity is the flow of electrons. Which way are those electrons flowing?
Negative to positive.
From negative to positive. So electricity is the flow of electrons from negative to positive. And that is called electron theory flow. E-L-E-C-T-R-O-N, theory. Electron flow theory. Yeah, we'll go flow. Hang on, let me erase that and write it nicely. We'll go with the electron theory flow. That sounds better. And that is from negative to positive. But then there's a conventional. Theory flow. Is the opposite. And here's why I'm going to tell you that. For a very long time, from about the discovery of this whole electron thing up until, I think, around the 1950s, everybody thought electricity went from positive to negative. And it was sometime around, I think it's 54, maybe I'm right or wrong on that, it doesn't matter. Somewhere, it wasn't that long ago is my point, with electron microscopes and whatnot, somebody realized that, hey, wait a minute, can't work that way. It's got to work the other way. It actually goes from negative to positive. For the reason I showed you that electricity goes from negative to positive because the like charges repel and unlike attract. So the true answer is going to be electron theory flow. However, because we go back in time and all the schematics and everything was drawn out in such a way, everything is drawn in conventional theory. So it doesn't matter to me if you're flowing something positive, negative, positive, as long as you know these two things, that there's electron and conventional theory, and which one is accurate and which one is not.
How does that affect us?
Huh?
How does that affect us knowing that?
Doesn't.
Direction?
Doesn't. They were wrong for all those years, and it didn't make a bit of difference.
Well, do.
Okay.
So, right?
Okay.
Stop it. Do you need to go outside?
Yeah.
Okay. So unless you're getting into digital electronics, it's not, for just basic wires and basic batteries and basic light bulbs, it's not a huge thing. If somebody wants to come into the class.
Kevin,
Yeah.
how we been doing?
Oh, hey, Robert, what's up, man?
I'm good. How you doing?
I'm doing pretty good. This is the 309 class.
Oh, yeah?
Yeah.
Hey, man. Oh, man, you got a fast forward, huh?
Are you still out at United?
Yeah.
All right.
Yeah, I ain't going nowhere.
This is one of our graduates. You working out at United now?
Yeah.
Last time I talked to you, you were
That's
working in the thrust reverser shop.
Yeah, I'm a sheet metal specialist.
All right.
I work in CNAs. So it's not.
All right. Back to this. We're recording. I believe we are. Okay. So anyway, we got that. So it doesn't really matter you have to understand it. All right. And as long as you understand
I
both.
just wanted to know that it didn't make any difference
If
if we're
it-
using basic electronics.
If I am troubleshooting something on a schematic, and I'll show you in the next class, it makes far more sense to troubleshoot it from a conventional standpoint, because that's the way the drawings are written. It's very difficult to go from negative and you have to find a ground point to another ground point back through. It's easier to follow it positive around the negative on a schematic. All right? So, yes. No, just scratching? All right.
Can you give an example of insulator? How is
Okay, so an insulator. What do we have? Helium. Helium has 2 protons and 2 neutrons. You can speak up now. All right. So how many electrons does it have? 2. How many can the first shell have? What's the most? 2, and it does in fact have 2. Does that have more than the half of the allowable or less than half of the allowable? It's way more than half. What's half? 1, and it's got 2, so it's got twice as. So this would be an insulator.
The best insulator.
All right. So what are some common insulators that we work with? Plastic, glass, wood, water. Pure H2O, I think, is an insulator. It's the stuff inside. Yeah? Okay. Okay. Let's take a break, and when we come back, we'll start to get serious.